Let us next consider this example which illustrates the difficulty that we discussed about in the previous video. Namely that whenever you have a ring homomorphism F from A to B, then the ideals of A do not behave well when they are extended with respect to the homomorphism. For example, here you have these two rings. This is our usual ring of integers and this is the ring of Gaussian integers, which are which consists of all the complex numbers a plus iv, where a and b are both integers. And the embedding is just your usual inclusion map. It takes any integer and gives you that integer back as output. For example, if you choose the integer 2, say, then the image of 2 under this map is 2 itself, which of course can also be interpreted as 2 plus I0. The real and imaginary parts are both 2 and 0, which are both integers. So it belongs to this. Now this is the difficulty. Ideally, what we would have liked, that if you take a prime ideal from this domain ring, then its extension should also be a prime ideal. That's not necessarily true. A prime ideal of Z may not stay prime when extended to Zi. And actually we know precisely what the prime ideals of the ring of integers are. They are the principal ideals generated by the prime numbers. So let us see what the possible cases are here. The first prime of course is 2. So this 2 within round brackets is the principal ideal generated by 2 in this ring. So you know what its extension means in this ring, and that extension turns out to be the square of the principal ideal generated by 1 plus I in the ring of Gaussian integers. This is itself not prime. Okay, instead it is the square of a prime ideal in Zi. The prime ideal is this. The principal ideal in Zi generated by the complex number 1 plus I is prime, and this extension turns out to be its square. But then next we have the odd primes, and odd primes come in two classes. Those which leave remainder 1 when divided by 4 and those which leave remainder 3 when divided by 4. So the primes that are of this type, for them if we similarly consider the extension of the principal ideal generated by any one of them, then that turns out to be the product of two distinct prime ideals in Zi, unlike this case where we have the same prime ideal whose square you are having as the extension. Here it is the product of two such distinct prime ideals in Zi, which are however prime, both of them. And for primes of this type which leave remainder 3 when divided by 4, this is the most favorable case that we like, because in this case the extension of this prime ideal is actually itself prime in Zi as well. Now let us next see how these statements are true. Let us first justify statement 1 like this. You take any integer m and consider its double 2m. Then this 2m is any element in the principal ideal generated by 2 in the ring of integers. Now you can express 2m like this. Minus m times 1 plus I times I times I plus 1 plus I, same thing. So what can you say about this product? Minus m times 1 plus I is a multiple of the complex number 1 plus I by another complex number after all. Minus m is also a complex number. So this first factor of the product belongs to the principal ideal generated by 1 plus I in the ring of Gaussian integers. This is another such element. This is also a multiple of 1 plus I or I plus 1 by a complex number. So it also belongs to the principal ideal generated by 1 plus I in Zi. So their product will belong to the square of those two ideals by the definition of square of ideals, or in general product of two ideals. So that means any element in this principal ideal in Z generated by the ordinary integer 2 actually is an element here as well. So obviously this is contained in this. Okay, this is a very simple thing. Now next what we do, let I be any ideal of the ring of Gaussian integers containing this principal ideal generated by 2. Then we notice this thing. If you take the square of the ordinary complex number 1 plus I have used square brackets here deliberately because I don't want to confuse this one with this one. Okay, round brackets have been consistently used to denote principal ideals, that is why. So if you do the square, you find that it is 2i, and this belongs to I. Why? The ideal I. But what is the reason? The reason is that we are saying here that I is an ideal of Zi containing this principal ideal. That means, that just simply means that I contains all the even integers, ordinary even integers. So I in particular contains the integer 2 as well, because I is an ideal, and that ideal is an ideal of the ring of Gaussian integers. So if you multiply 2 by any ring element, in particular by I, that product will also belong to the ideal. That's how 1 plus I square belongs to I. But when that happens, then it's an easy matter to see how we have this containment, that the square of this ideal 1 plus I mean the principal ideal, is a subset of I. How? Exactly how? I said easy, but exactly how? You take a general element of this square, how would that element look? That element, by the definition of product of ideals, will be a sum of products of two elements, one coming from the principal ideal 1 plus I and the other coming again from the principal ideal 1 plus I. So the general element in this square will look like this: some complex number times 1 plus I times some complex number times 1 plus I plus again some complex number times 1 plus I times some complex number times 1 plus I. So ultimately you see that it appears in the form of 1 plus I square times a sum which is after all a complex number. So because 1 plus I square belongs to this ideal, so if you multiply 1 plus I square by some other complex number, that will also belong to this ideal, but that is how the general element of this square looks. That is why this is a subset of I. But then what does it actually mean? It means that if I is any ideal of Zi containing this, then I also contains this square, which is itself an ideal which contains this. So obviously this will be the smallest ideal of Zi containing this, and that is why by the definition of extension this is equal to this. But you have to be careful with the details. Actually, what is the definition of extension? The definition of extension is this: you take I say you have two rings A and B, and there is a homomorphism F from A to B. Now you take an ideal, say anything, say J, of the domain ring A. What do we mean by the extension of J? First you apply the homomorphism F on J to get its image in the second ring F of J, which itself may not be an ideal. But the extension is the ideal in B generated by the subset F of J. In this case, what is that subset? Because we are dealing with the inclusion map, so it actually changes nothing. You apply the inclusion map on this ideal, this is our J now. the principal ideal generated by 2, you get that itself. But do not make the mistake of thinking that, oh, this is already an ideal. No. Then why am I doing all these things? It was an ideal in Z, not necessarily in Zi, because Zi is larger. Not necessarily means actually it is not. For example, what should an ideal do when you take any of its elements and multiply it by a ring element? The product should belong to the ideal. Now you take 2, for example, the number 2, the integer 2, and multiply it by this new ring element, because now your ring has got larger. 2i. Is 2i an even integer? No. So then how is it an ideal? So the extension actually is this. Next comes the question of how it is that this principal ideal generated by 1 plus I in Zi is a prime ideal. That thing is the next thing. So here you have to use some already proved things from Herstein's topics in algebra 2nd edition. By the solution to exercise 8 of section 3.8 from Herstein's book, we know that 1 plus I is a prime element in Zi. And that is why the principal ideal that 1 plus I will generate in the ring of Gaussian integers will be a prime ideal. Actually, it will be a maximal ideal, and that is why it will be a prime ideal. But again, by lemma 377, actually what is going on here? How does primality of the element 1 plus I in Zi imply that the principal ideal it generates will be maximal and hence prime? That comes from the fact that this Zi is a Euclidean ring, and in a Euclidean ring, the prime ideals are precisely the maximal ideals, I should say, are precisely those principal ideals which are generated by prime elements. That is why these things are happening. So that's how we have seen that whatever the author is saying in the first statement are true. Next we go to statement 2. In the second statement, we consider primes of this type, those which leave the remainder 1 when divided by 4. Now there is a famous result about this type of primes which was proved by Fermat. It's a result from number theory which is available as theorem 382 in Herstein. By that result, such primes are always expressible as a sum of two squares of integers, and it's pretty easy to see why both of those integers have to be non-zero. So that's how our p is equal to a square plus b square for some non-zero integers a and b. Also, because of this fact and exercise 8 of Herstein, the thing that we mentioned just now, these two complex numbers a plus ib and a minus ib are both prime elements in Zi. In the solution to exercise 8, there actually that problem is about precisely determining what the prime elements in the ring of Gaussian integers are. So these are prime elements. There are other types of prime elements also, but these are prime elements if this happens. And then one can pretty easily verify that the extension of this prime ideal generated by the prime p in the ring of integers is equal to the product of these two principal ideals, one generated by a plus ib and the other one generated by a minus ib in this ring. Just keep one thing in mind, that this p that we are seeing here, the principal ideal generated by p, when you calculate the extension, you have to consider the image of it under the homomorphism, which luckily in this case is just this ideal itself, because the homomorphism is the inclusion map. So using that, you can very easily show that this thing is true. And now here, because of the primality of these elements in Zi, these two principal ideals are both prime ideals in Zi. That's how we have the extension in this case as the product of two prime ideals in Zi. And they are also distinct because both A and B are non-zero. I have left some things not quite explained here in full details, but that is because I want you to supply the details. Okay, so please try this part. For example, you have to, this is just a matter of seeing that there is a result which immediately gives us this. There is nothing else to it. But then you have to go back to Herstein's exercise 8 and see how these things are prime elements because of this. That is one thing you have to do. Then you have to actually verify this. And then these ideals will be prime, that comes from the primality of these complex numbers as elements in Zi. And then you also have to see why these are distinct. And the reason is given to you because A and B are both non-zero, but exactly why. So that you have to figure out. And finally, let's go to the third statement. And finally, we have 3 in which P is a prime that leaves remainder 3 when divided by 4. P is congruent to 3 modulo 4. Then from the characterization of all the prime elements in the ring of Gaussian integers, we find that P is a prime element. This type of primes are all prime elements in Zi. And then this is one fact that you have to prove. In this case, the extension of the principal ideal generated by P in the ring of integers is actually equal to the principal ideal generated by P again, but now in the larger ring, the ring of Gaussian integers. This is something you have to prove. It's not very difficult, you try it. Okay, but then how is it that this is a prime ideal? Because it is being generated by a prime element in Zi, and prime elements generate maximal ideals in a Euclidean ring, and those maximal ideals are automatically prime ideals. That is why. And with this, let me just end this video. There is, I think, another 1 or 2 results, and then there are some exercises. Not the ones that appear after the section. Within the section itself, there are some exercises, and then only it will be complete. So see you next week with those results. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.